This is our last lesson on the intersection of lines and planes. We've already done how a line touches a plane, which you can go through just one spot, so you'll get one solution. Or the line lies on the plane, which is infinite solutions. Two planes intersecting, so that will intersect along a line, kind of like you see here in this picture. Oh, you can't see my mouse. You can see it in this picture here. And then today we're going to do three planes, which is really good because three planes, well, if planes have three variables and now we have three equations for three planes, hopefully we'll get one solution or a unique solution. Before we get into that, let's talk about what a consistent solution is, or a consistent system is. A system is called consistent if the possible solution satisfies all of the equations. So the solution you found, if you were to plug it back in, it would satisfy everybody. You get like left side equals right side. So if you have a consistent system, it can look one of four ways. It can be either they intersect at a point. So the way that they are oriented, they meet in like a little corner almost, not a perfect corner of 90 degrees. It can, but it doesn't have to. The other option is that they meet along a line. So much like we did for two planes, they might just be revolving around a line, which is it's a special case, but it can happen. And the last two are kind of more specialty cases. Because you have planes, if you have two of the planes that are coincident, so they're lying on top of each other, they can still interact with the last plane. So in this case, you have the two planes, 1 and 2, that are on top of each other. Well, then they make a line with the last plane, as long as the last plane is a little bit different. And that's just the intersection of two planes almost. We know how to do that from the last lesson. And then the last case is, well, what if all the planes are actually just the same? What if they're all coincident? They're just scalar multiples of each other. Well, then you have infinite solutions, just like you do for case 2a and b. But this one's a planar solution because all the points in the plane instead of all the points on the line make it the solution. There's just some notes about it that I wanted to give you guys just for little facts. Case 1 and 2a will never have the starting planes as coincident or parallel. Okay, just something to check for. You always want to check for parallel and coincident because there's usually have little shortcuts to them. So if you don't have that, it's a normal solving question. You make your matrix and you solve all the way down. Unfortunately, you cannot distinguish case 1 from 2a if you're solving. They will look like three non-coincident, non-parallel planes, and you'll solve them. It's just that if you do get to 2a, I'll say in a second what's really going to happen, but you'll notice something if you try and solve 2a. For case 2b and 3, you can very easily tell that it's these two because there's coincident planes. You just check the Cartesian equations. You will notice that they are scalar multiples of each other. Then you can immediately say that either, well, two planes are coincident, so there must be a line solution, or all three planes are coincident. Therefore, there's a planar solution. However, just to go back to 2a, if you are solving 2a because you don't know what the answer is going to look like, because there's infinite solutions along a line, what's going to happen is you're going to run into 0x equals 0, or any of the other letters, 0 equals 0. That is your indicator that's a straight line because this is the indicator of infinite solutions. Once you reach this point, if you get 0 equals 0, you just use your parameters to solve. Okay, you let your z equal t, solve for y, solve for z, or solve for x, and then you can go from there. If case 2b occurs, remember you are going to be given three planes. And since two of them are just going to be the same, you, for all purposes, only have two planes. So you're trying to solve the intersection of two planes. You just need to follow the last lesson, lesson 3. How do you find the intersection between two planes? It's a straight line by default. So how do you write a straight line in parametric form? If case 3 happens, you're very happy because there's almost no work to do. They all lie on top of each other. There's no solving. All you need to do is instead write the plane given one of the three. They're all technically the same. Write it in parametric form. And that's it. Just remember that every solution, unless you get concrete numbers, should be written in parametric form. Now, these are for consistent systems, though. So there is a solution, and the solution works for everybody. That is not always the case, though. So a system is called inconsistent if the possible solution you're finding does not actually satisfy all the equations, which has happened to us before. We have solved some stuff all the way down. We got a solution, but we check it in some third equation, and it doesn't work. So that can happen if the planes are arranged in a triangular prism. Now you're not going to know this, but this is just one of the options. I'm just letting you know that this is one of the options. Now you can see that it's inconsistent because if you take this line 1 here, line 1 touches plane 2 and plane 1, the blue and the green one, but this line does not touch the third plane whatsoever. So it would be a solution to planes 1 and 2, but because it doesn't work for plane 3, it is inconsistent. Then we get into a bunch of parallel coincident examples. This next one is if two of the planes are strictly parallel. They are not coincident, which is really important. So same idea. You have the green line and the blue line, but the green line and the blue line don't touch. There's a big gap between plane 1 and 2. Because not all of the planes intersect at the exact same spot, it is inconsistent and very easy to check for, just as case 3. Case 3 has 3 parallel planes, so nobody touches anybody. There's super not a solution. This one you could get a solution, but it's not going to work in the last one. And this has kind of always been the case. If you have strictly parallel lines or planes, they will never touch. There is never a solution to those guys. The last one is more of an annoyance than anything. If two planes are coincident, so those two lie on top of each other, and then the third one out is parallel to those guys, well, you got a gap again. So if there's ever a gap between any of the planes, you immediately have no solution because there's no consistency. The only time that doesn't happen is if you have case 1 where they all intersect, but it's pairwise intersection. So 1 with 2, 1 with 3, 3 with 2, but not everybody all at once. So if you ever get case 2 or 3 or 4, where you notice that 2 of the planes are strictly parallel, then you know there's no work to be done because there's not a solution. The thing to remember is that you need to check the normal vectors. So the normal vector is found by looking at the coefficients of the equation. It's the constant term that's left out. So the normal vectors or the coefficients will all be scalar multiples, but the constant terms will not line up with each other. So if you multiply an equation by 2, everything will be multiplied by 2 except the constant term. So that will tell you something is parallel, and that is what you get happy because there is no work to be done. Unfortunately for case 1, you cannot distinguish case 1 from the other 2 cases at the start. So I said earlier that these 2, you cannot distinguish them just by looking at them, or at least I can't. Maybe there's a way to do it. This one will be the same. Nobody's parallel, so there's going to be no tricks. You're just going to solve it, and unfortunately, it's not going to work. And you'll know it's not going to work because I didn't write it exactly word for word here, but before you would get 0x equals 0. But if this is the case, you're going to get 0x equals 5, for instance, which nothing times 0 will give you 5. So there is no solution for that one. Then again, you just stop at that point. You know the rest of the system is not going to work. Now, if you are told somehow that there is no solution, then you can automatically tell me that it is case 1. Now, that's not true in general. If I told you there's no solution, I just told you there are 4 different cases. But if for whatever reason you know, what your process always is you always check for parallel or coincident lines at the start, because that is how you eliminate half the work you have to do. And again, somehow if you know it, then you immediately know they must make a triangular prism because you've already checked for parallel in coincident planes. So that's just something to keep in the back of your head, is that if you know it, it'll make a triangular prism. That's like a typical test or assignment question. Okay, so let's actually do the work to it now. So we're going to determine whether a solution is possible. If it is possible, what kind of solution? Are we getting a line? Are we getting a plane, infinite, or unique? So your first thing, always go through, check for any scalar multiples. So like from 2 to 4, that's multiplying by 2. Okay, doesn't work for the y's though. But if you skip to planes 2 and 3, plane 3 is just double plane 2, which this means coincident. Now, since this third plane is not coincident and it is not parallel, So I've checked those x and y's. We already determined those do not match up. They are the only two that are 2 and 3. That means what you're really doing is intersection of 2 planes, because these two are the same. They're just multiples of each other. So you really have plane 2 and plane 1. Oh, how do those two intersect? You get, that's supposed to be an infinity symbol. You get infinite solutions. So there is a solution possible. There's infinite of them. And then it's a straight line. Okay. So next one, same thing. Check for multiples and see what can happen. So let's see. From this one, I multiply by 3. I multiply by 3. I multiply by 3. Okay, that's good. With the other one, let's just check. I multiply by 3. I multiply. Oh, excuse me. There's a typo right there. That is definitely supposed to be a y. So by this one, I multiply by 3 to get 3x, and then I multiply by 1. Okay, those guys are not parallel. Now, what you have to notice on this guy, for plane 1, plane 2, only the normal vectors. This is the proper way to say it. Sorry, this is actually 2. Normal vector 2 is equal to 3 times normal vector 1. And when I write only normal vectors, that means that the constant term on the end here, those guys are not scalar multiples of each other. So plane 1 is strictly parallel to plane 2. That means everybody's not touching. No solution. Done. Now, if you did get example A, you would be going farther in the question. If you got question B, that is the last thing that you need to put. Okay, so let's check for some more. 4 to 4 is just 1, negative 2. Okay, that guy, we're not multiplying by anything here. From 4 to 3, multiply by a fraction, but this one's doubling. So that if that's doubling, negative 2ing, I guess, it just, nothing matches here. So in this case, there is no parallel or coincident. Coincidence. So there's a possible point of intersection. So it could be a point or line. Those would be the two possible solutions. There might not be. That's the important thing here, because it could make a triangular prism, but I just can't tell. So this is example case 1 of a consistent system, or case 2. I don't know what it's going to look like. Or it's also case 1, but of the inconsistent system. Okay, on this guy. So to go from 1 to 2, multiply by 4, multiply by 4, multiply by 4, multiply by 4. Okay. Plane 2 equals 4, plane 1. And then the other guy, plane 1 and 3, multiply by negative 8, negative 8, negative 8, negative 8. Plane 3 equals negative 8, plane 1. And that by default means that plane 2 and 3 are also scalar multiples of each other, mainly because they both come from plane 1, but you can see multiply by negative 2, negative 2, negative 2, negative 2. So this means all coincide. Therefore, infinite solutions, and it's a plane. It's not a straight line, it's a plane solution. Okay, so that's how you can tell. B was the only one you didn't have to do any work. D, you also don't have to do a ton of work. You just need to transform this equation into parametric form. Let's see what we can do out of this. So we're going to find the points of intersection if it or they exists. So we have three equations. I don't see anybody that's a scalar multiple of each other. So let's throw this guy into a matrix and let's try and solve them. See what happens. So 1, -1. 1, augment it with -2. 2, -1, -2, -9. And then we've got 3, 1, -1, -2. So let's try and do 2 steps in one just to kind of save your space. Let's get rid of row 2. Not row 2, obviously the first entry in row 2. So let's make row 2 equal to, we got double the first row and then subtract the second row. So my first row is going to stay the same. We very rarely change the first row unless you need to multiply it. Okay, so double the first row, subtract. 2 minus 2 is 0. -1 minus, sorry, -2 was multiplied. Minus -1 is actually back to -1 again. And then we have 2, because we multiply that by 2, minus -2 would give us 4. And then -4 minus -9 is 5. Okay, but remember, we want the triangle. We want this guy all to be 0, and we can do that first by also making that 3 and 2 is 0. So let's change row 3 at the same time. Row 3, we can triple the first row and then subtract the third row. So the first, that should be 0, as intended. -1 times 3 is -3. Minus 1 is -4. Then we have +3 minus -1, that is 4. And then -6 minus -2 is -4. Okay, then we got one more go. We got to make this last guy into a 0. So let's quadruple. Let's take row 3 and make it equal to, we're going to quadruple the second row. And then same symbol, so we're going to subtract the third row. First row, same. Second row, same. Third row, the zeros. Again, that's why you always do, for this last one, you always do the second row with the third row, because these two zeros are always going to make 0 again. We don't want to change this entry from a 0. This will also be 0 because you're going to turn this into a -4 by multiplying. Subtract -4 will be 0. Then we got 16 minus 4, which is 12. And then we're going to get 20 minus -4 is 24. So from here, what we need to do is then solve this leftover guy. So what this guy tells you is that 12z equals 24. Well, it's nice and easy. Z must equal 2. And then what you do is you keep chucking backwards now. So you found that z is 2. Let's go back into the equation up here. This is that -1, so -y, plus 4z's, oh, but z is 2, equals 5. So plugging my z up in here and then rewriting the second line. Well, that's going to be 8. 5 minus 8 is -3, but bring that negative over. Y equals +3. So we've got our z, we've got our y. Throw it back into the very first equation. A single x minus a y, so -3, plus the z, plus 2 equals -2. So that's -1 on this side, plus it on the other side. X equals -1. So negative's not very big. There we go. And because you got a unique point, POI is written as a point, -1, 3, and 2. It's going to happen sometimes, not going to happen all the time. It's very rare that we're going to get just one number, or 1 point, I should say. So the next example, same idea. We're just going to go if we can. So check for any multiples. I'm not seeing any multiples. Like 3 times 1 is 3, but then it doesn't work for the y's. You got to multiply by 5. Nothing else to multiply by 5, blah, blah, blah. Okay, so what we need to do then is just put it into a matrix. Maybe I'll start down here again. So we're going to get or you know what, I'll start one up here just because we're going to have to multiply these equations. I can definitely see where you have to multiply. So let's do 2, negative 1, 1, augmented with 1, 3, negative 5, 4, augmented with 3, 3, 2, negative 1, 0. So what I'm going to want here is I'm going to want everybody to be the same. So I can start doing my elimination. Now I'm very, very fortunate that my 3's actually line up. So all I got to do is I got to triple row 1. And I got to double row 2. And I'll just put a little comma here. We also need to double row 3. And then everybody matches, which is very fortunate. Otherwise, you got to do a bunch of other multiplying. So then we get 6, negative 3, 3, and then 3. Doubled is 6, negative 10, 8, 6, 6, 4, negative 2, 0. So this is kind of our starting matrix. So now we can do adding, subtracting. I can definitely do that row 2 equals row 1 minus row 2, and row 3 equals row 1 minus row 3. So the first row will stay the same, 6, negative 3, 3, and 3. And now we're going to subtract first and second. So 6 minus 6 is 0, as it should be. Negative 3 minus negative 10 is 7. 3 minus 8 is negative 5. 3 minus 6 is negative 3. And then we're going to get first and third. So 6 minus 6 is 0. Good. Negative 3 minus 4 is negative 7. 3 minus negative 2 is 5. And 3 minus 0 is 3. Okay, now something to notice here is your equation 2 and 3, or your row 2 and 3, I should say, are scalar multiples of each other. So they weren't scalar multiples to start with, doesn't look like, but they did turn out to being after doing a little bit of row reduction. So this, I can immediately tell you, is going to give me infinite solutions because they are scalar multiples of each other. Just to show it fully, if you didn't notice that, that's fine. There's a lot of numbers going on. You just do, okay, well, row 3, let's do row 2 plus row 3, because that's how I would get my 7 here to be a 0. So 6, negative 3, 3, 3, 0, 7, negative 5, negative 3, 0, 0, 0, 0. So what does this mean? This means 0z equals 0, infinite solutions, as I said. Now we know this, though. None of the initial planes were coincident. That's usually how you get some sort of infinite solution. Because they are not coincident, we know that this must be the case of 2a. So I'll just take it back. 2a is the case where they all revolve around a single line, because none of these are parallel or coincident. Why you need to know that is because that tells you how to do the rest of it. So that means you're going to have to introduce a parameter at this case. Now, if you ever get 0z equals 0, you should be doing a parameter. So what we can do is let z equal t, and then you kind of carry on, just as if you had a number. And like in the last example, we had a number. So you figure out the solution, which is t in this case, and now you sub backwards. Okay, so 7y, 7y minus 5z, so 5t, equals negative 3. Y would equal, we're going to bring the 5 over, we're going to get negative 3, but we're going to divide it by 7, so over 7, plus 5 over 7. Okay, plugging backwards some more. I'm going to switch it up here because I know it's going to take a little bit to write this out. we can then write the x. Now, you can make your life a little bit easier. The last x we had was 6, negative 3, 3, 3, whatever. You can always go back to the start. All these things are elementary row operations, and elementary row operations make equivalent systems. So you're allowed to plug it in at any point because all of these equations are equivalent. So we have 2x minus y. Well, y we found is this big ugly guy, negative 3 over 7 plus 5 over 7t plus z, which is just t, equals 1. And we'll do the math out just to see it. 2x plus 3 over 7 minus 5 over 7t plus t equals 1. 2x plus 3 over 7. If that's negative 5 over 7, that's 7 over 7. And then you get 2 over 7. Plus 2 over 7 t equals 1. So 2x equals, well, I know it's going to be minus 2 over 7t. 1 minus 3 over 7 is 4 over 7. Divide everybody by 2. Well, 4 divided by 2 is 2. And then 2 divided by 2 is 1. So minus 1/7 t. Usually it's very nice of you to write them all in a row. I don't really have the space for it, so I'll just box them off. There is the parametric solution. Z is t, y is a bunch of fractions for the t, and then x is a bunch of fractions for the t. Notice that you only have one parameter, it's t, because it's a line solution. Lines only use one parameter because they have one direction vector. Okay, for this next one, it unfortunately not very nice. There's nice in terms of there are no coincident or parallel planes. We love that because it really reduces the amount of work you have to do. But let's just try it one more time. So we've got 1, negative 1, 1, and 1. 1, 1, 2, 2, 1, negative 5, negative 1, 1. Oh, that was not a good idea. Okay, so now we have to row reduce this. So this actually looks not so bad because we just got a bunch of 1s again. So I can do row 2 is row 1 minus row 2, and row 3 similar. Row 3 will just be row 1 minus row 3. So we'll get 1, negative 1, 1, augmented with 1, 0, negative 2, negative 1, negative 1. And then we'll do the last row. We'll get 0, 4, 2, and 0. Okay, let's go one more time. So I can see that row 2, or 3 rather, if I double row 2 and I add row 3, that would make this guy right here 0. So 1, negative 1, 1, 1. 0, negative 2, negative 1, negative 1. And then negative 2 times 2 is negative 4 plus 4 is 0. And of course, the first one is 0 because there's just zeros. And then I get 0 again. And then I get negative 2 plus 0 is negative 2. So this is 0z equals negative 2. There is no solution. So now you don't have to do the back substitution. I didn't ask you for it, but as I said before, if you do not have parallel or coincident planes, but you still do not make a solution, it's a triangular prism, is the orientation of these planes. Okay. So for this one, what we're going to have is we're going to have, it looks like some coincident planes. So to go from equation 1 to equation 2, we have times by 4 times by 2. Oh, sorry, I'm looking at the wrong one. Equation 2 and equation 3 times by 2 times by 2 times by 2 times by 2. That last one is not parallel or coincident to any of the other ones. You can even tell with the 1 to 5 and the 1 to 1. It doesn't work out. But you have to remember this. So because these two are coincident, you don't need to make a huge system. So just use 2 planes. And when you're using 2 planes, you are not choosing the coincident planes. For instance, I don't want the one with big numbers. Cross it off and just use the first 2. We know because they're 2 planes, you have to have a line solution. So this goes back to the last lesson where you write your matrix 2, 1, 1 with 1, 4, -1, -1, 5. You know this will never have a unique solution. It's never going to be a bunch of numbers. It's going to be a parameterized solution. And again, we know that because the solutions align. So for this one, we can double R1 and then we can just subtract R2 to get 2, 1, 1, 1, 1. And then you will get 0, 3, 3, -3. Now, there's no triangle to make, that special triangle. So all you can do is hope to get this 0, and that's all you can do. So what we do at this point is we're not really getting a solution again. So what we can just say is let z equal t. So if z equals t, that means 3y from this last equation plus 3t equals -3. And if you divide everyone by 3 and then just bring them to the other side, you get -1 minus t. So here is your first parameter for y, your second parameter equation for, for z and y. And then plug it all back to the start. 2x plus y, which is -1 minus t, plus z, which is just t, equals 1. And this one is a little strange to look at, but it happens. Your t and your t cancel. And then you get 2x equals -1 turns into +1. So 2x equals 1. Seems strange, but remember the parametric form of an equation doesn't have to have a t in it. It just means that one of the components was 0 of your direction vector. That's not a big deal. So then you have x equals 1. So if you wrote it in the parametric form, which I usually like it when you do just for clarity, you get x equals 1, y equals -1 minus t, z equals t. And it's because there's a bunch of zeros here, plus 0t, 0 plus. They're not necessary in this solution, but that's where all these missing things are, just a bunch of zeros. So that's the lesson. So it's very important to know what the solutions are going to look like because it kind of informs you on, are you doing a line equation? Are you doing a plane equation? I should maybe do an extra example. I'll do kind of just a bonus example here. If you have 3 planes that are coincident, so 3x plus y plus z equals 1, 6x plus 2y plus 2z equals 2, 9x plus 3y plus 3z equals 3. They're all coincident with each other. So you just need to change the thing to say to be in a parametric form. Okay. So to do that, I will let you do it. Good review. Okay. The video is too long by itself anyway. Okay. Congrats, you're done calculus.